Okay, this is the second part of module 4, wherein we're going to focus on the different measures of variation. And under that, we have range, and we also have the variance, and standard deviation, and then the applications involving coefficient of variation. Then we're also going to add the empirical rule. Okay. Now, as we proceed, okay, the first measure of variation is what we refer to as the range, which is simply the difference between the largest and the smallest observation. And this is the same concept we have introduced in the previous modules. Okay, we're in the range. We simply subtract the largest value minus the smallest value. However, the range is not a very good measure of variation because it ignores the way in which data are distributed. And let us illustrate that by the two data sets that we see here. Okay, so the first data set that we see on the left, we have the values that is 7, 8, 9, 10, 11, and 12. And the highest value is 12, and then the lowest value in this data set is 7. So by computing the range, we get the range to be 12 minus 7, and the range is equal to 5. Okay, but notice how the data values are distributed. Okay, so the values are evenly spread out in this data set. All right, now let us shift our attention to the second data set that we see at the right, wherein we have 7. There's only one 7, 10, then we also have 11, and then there are 3 12s. Okay, and the highest value is 12 in this data set, and correspondingly the lowest value is 7 in this data set, which is the same as the previous set that we have illustrated. Therefore, the range will be 12 minus 7, and the range is also 5. Okay, however, if you're going to examine further the distribution of the second data set that we have, right, most data values are clustered towards the right end of the distribution. Okay, and this is what the last statement indicates, that the range ignores the way in which data are distributed. Okay, thus the range is not a very good measure of variation. Okay, and another measure of variation that we may consider is what we refer to as the variance, which is actually an important measure of variation because it shows the variation about the mean. When we say variation about the mean, okay, by looking at the formula that we have here involving the sample variance and the population variance. So for the sample variance, we have S squared, and that is given by the summation of the square, okay, of the differences of the mean, okay, and the given data value in our data set. Okay, that means to say, all right, we are getting the distance of each data value from the mean of the distribution, okay, by subtracting the two of them, and then we square each of those difference, okay, and then we get the sum because we see here the summation notation, all right, and we divide it by n minus 1, okay. Now comparing it with the population variance that we have, wherein if the data is taken from the population, then we have the sigma notation, okay, or sigma squared is equal to the summation of the difference, okay, of each data value from the mean, and then we square it, okay, and we divide it by our capital letter N. And when we say the variance, okay, take note that we are referring to, these are what we refer to as the squared deviations, okay, from the mean, okay. That's because the distances, okay, or the differences of each data value, okay, from the mean, as indicated by this following expression here, okay, are being raised to the power of 2. Okay, thus we refer to it as squared deviations from the mean. Okay, now, however, right, if we are going to examine it further, when we say squared deviations or squared distances from the mean, okay, for example, if our data set, okay, is expressed, or an original data set is in terms of, let's say, inches squared, or let's say in terms of inches, all right? And if our data set has something to do with, let's say, the heights of the different students in a Psych 101 class. All right, and they have to be measured in terms of inches. And if I'm going to describe my data set, okay, using the variance, then I will be describing our data set, which is in terms of inches. All right. If I'm going to make use of the variance, I am now going to interpret it, okay, using inches squared, because we are referring to squared deviations from the mean. All right. So if looking at it, okay, if our data set is in terms of inches and explaining it or interpreting it in terms of the squared values, that is in terms of inches squared, okay, we may lose the meaning, right, because we are not interpreting our data in the original unit of measurement. Okay, that's why the variance is not usually reported, okay, when we do analysis of our quantitative variables, but instead we make use of another measure, which is actually derived from the variance, okay, which is what we refer to as our standard deviation. Okay, now we will go to standard deviation in a while. Now going back to our formula, right, if you notice for the sample variance, the denominator that we have is n minus 1, okay, and in our population variance, the denominator that we have is our population size, which is capital letter N, all right? Now, we use the denominator for our sample variance to be n minus 1, that is to avoid biases, okay, or the errors committed when different samples are chosen in a given population, all right? Now, let me proceed, okay, to the next slide. Okay, because if you are going to look at our formula, okay, if our data set, let's say for example, you have 100 data sets, okay, then that means to say your x sub i's will be ranging from, that is from 1 up to, let's say, 100. Okay, so applying our formula, then here you will have to subtract the mean, okay, from the data value, okay, let's say from x sub 1, okay, subtract the mean also from x sub 2 up to x sub 100. So you are going to repeatedly perform this procedure 100 times, depending on your sample size or depending on your population size. And if you're going to do that, or if you're going to use that, it will be impractical to do so. Okay, therefore, we are going to utilize, okay, a technique which is what we refer to as the raw score method, which will be used later on to compute for the standard deviation. Okay, now relating to what we have indicated earlier, that with the concept of the variance, because as what we have emphasized, that the variance is referring to squared distances or squared deviations from the mean, all right? And coming up with or manipulating it further, we will arrive to what we refer to as a standard deviation, which is actually the most important measure of variation. That's why oftentimes you would encounter interpretations for quantitative data using standard deviation instead of the variance, because it shows the variation about the mean. And take notice of this, that it uses the same unit, okay, of measurement as the original data. Okay, that is because if you're going to look at our formula, the expression that we have inside the radical symbol or inside the square root sign is simply the formula that we have for our variance. Okay, and to get the standard deviation, we simply take the square root of the value that we have for our variance. All right, and observing also from the population standard deviation formula, the expression that we have inside here is our population variance. So simply getting the square root of that will give us the population standard deviation. Okay, now this is where this statement would come in. Okay, we're in the same unit, okay, of measurement will be used to interpret, all right, as the original data. So going back to our example, if our original data is in terms of inches, okay, so if I am going to use variation, okay, to interpret my data, then the unit will be expressed in terms of inches squared. Okay, that is because if we will go back to our formula, okay, the variance is squared, okay, deviations from the mean. All right, so the interpretation that we will have based on the original data that we have in the data set, which is in terms of inches, will now be interpreted using inches squared. However, if we take the square root of that, okay, so the square root of inches squared will now be equal to inches. So meaning to say, we are now interpreting our original data in the same unit, okay, which is in terms of inches, because we have taken the square root of our variance. Okay, so basically the standard deviation of the sample data is the square root of S squared. In the same manner, the standard deviation of the population, which is now expressed in terms of sigma, is the square root of sigma squared, which is ang sigma squared or ang S squared that we have with the expression inside radical symbol is our variance. Okay, now as what I have pointed out earlier, okay, that if we have 100 data sets, then you will be subtracting, okay, the mean from that data set 100 times. Or let's say, for example, if you have 1,000 data values in your distribution, then you will be performing this procedure, okay, 1,000 times, and it will be impractical to do so. Okay, therefore, we introduce, okay, this method, which is what we refer to as the raw score method. And how is this done? The raw score method is given by the following formula. That is S squared, as what we have indicated. This is our sample variance, and that is given by N, okay, times the summation of the square of each data value. Take note of that. Okay, minus the square, okay, of the sum of all data values. And we divide everything by N times N minus 1. To illustrate the use of this formula, let us refer to the following data set that we have here. So we have in the first row, we have the X sub i's, okay? And there are 10 data values that we have. And in the second row, we have the squared values of each data value that we see in the first row. So if I am going to sum up the values in the first row, I will have the summation of all X sub i's, which is equal to 506. If I am going to sum up all the values that we see in the second row, okay, and then that will be the summation of the square of all X sub i's will give us 26,972. Now, using our formula, okay, we plug in the values. So going back to our table, our N here is equal to 10. That's because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right. So using our formula that we see on top here, okay, that is S squared is equal to N. Our N is 10. Okay, this is our N. And this is the summation, okay, of all X sub i's. Okay, wherein we are taking the square, okay, of each data value. So that is the sum of all squared values, okay, in our data set. And that is given by this value, which is 26,172, minus, okay, the square of the sum. Okay, so we get the sum of all data values and we square that. And that is taken from our first row. The sum of our first row is 506. Okay, then squaring it, we get 506 squared. Divided by, that is our N is 10, and 10 minus 1 will give us 9. Okay, so summing this up, okay, or simplifying this, you can utilize your calculator. We will end up with 13,684 over 90, and the variance will be equal to 152.04. Now, remember that our standard deviation, okay, is given to be the square root of our S squared. And if our S squared is equal to 152.04, solving for our standard deviation S, we simply take the square root of 152.04, which is in this case will be equal to 12.33. So from the data set that we have, the standard deviation is 12.33. And the variance will be 152.04. Okay, so if in the learning task or in the quiz or even in the exam, if you are asked to use the raw score method, then you have to utilize the formula that we have here. Okay, now we continue. All right. Let's examine the different data set that we have here. Okay, because if you notice, the mean of the first data set or data A, the mean is 15.5. The mean of the second data set or our data B is also 15.5. Okay, and the mean of data C is also equal to 15.5. However, if you notice how our data values are distributed, okay, they are all not the same. So how come the mean values are all equal for all three of them when in fact they are distributed differently in each data set? Okay, so let's examine that. So if you notice, the standard deviation of data A is given to be 3.338. Okay, the standard deviation of our data B is equal to 0.9258, which is smaller compared to the standard deviation of our data A. Okay, and in the same manner, the standard deviation of the third data set is 4.57, which is the biggest, okay, or the largest among all three of them. But if we're going to examine our data A, B, and C, okay, we refer to the data set wherein the standard deviation is the least, okay, and that is taken from our second data set or our data B, okay, because the mean is 0.9258, which is the smallest among all of them. So let us observe, okay, how the data values are distributed in data B. So notice our data values are clustered in this region, okay? So there's only 114, there are 315s, there are 316s, and there's 117. So if you notice, the values are consistent, okay, or close to one another. Okay, therefore, the standard deviation that we arrive at is the least among all three of them. Okay, now, if we look at the standard deviation of the third data set, okay, which is in this case is 4.57, we notice that this is the greatest, okay, or the biggest standard deviation compared to all three of them. And by observing how our data values are distributed in data C, okay, so we have 11, 11, 11, then we have 12, then we have 19 to the far right end of the distribution. We also have 20, 20, and 20, okay? So the values are extreme, okay? We have values at the far left of the distribution and also values at the far right of the distribution. That's why we end up with standard deviation, which is the biggest among all three of them. Okay, so what does it tell us when the standard deviation is small? Okay, what does it indicate if the standard deviation is big or is huge? Okay, so the smaller the standard deviation, okay, the more consistent or close your data values are. All right, in the same manner, the bigger the standard deviation, okay, the more dispersed, okay, or the more varied your data values are in your given distribution. Okay, so I hope you keep that in mind when we do interpretation of standard deviations, okay, depending on the set of data that we have. Okay, now let us proceed. Now let us continue to what we refer to as the coefficient of variation, okay, which is an application of the different measures of variance. All right, and here when we talk of coefficient of variation, which we simply denote by CV, okay, is a measure of relative variation, which is always expressed in terms of percentage, and it shows the variation relative to the mean, okay, which is actually used to compare two or more data sets that are measured in different units, okay, and that is given by, okay, our CV is computed to be, we have our standard deviation, okay, divided by our mean, okay, and we multiply it by 100% because we need to express in terms of percentage. Okay, now let us make use of this formula to illustrate further, okay, the concept of coefficient of variation, or what we refer to as CV. Okay, when we talk of CV, all right, or the coefficient of variation, in the field of business, okay, this allows you to determine how much volatility or risk you are assuming in comparison to the amount of return you can expect from your investment. And we keep in mind that the lower the ratio of the standard deviation to the mean return, okay, that means to say, the lower the CV that we have computed, the better is your risk-return trade-off. Now, what do we mean by this risk-return trade-off? Risk-return trade-off indicates that higher risk is associated with greater probability of higher return. And consequently, lower risk with greater probability of smaller return. Okay, so we keep in mind that the smaller is the percentage, or the lower the ratio of the standard deviation to the mean, or meaning to say the lower is our CV, okay, the better would be your risk return trade-off. Okay, let's put this into application. Now, let's say I have stock A with an average price last year of 50 US dollars with a standard deviation of 5. Okay, then I also have stock B, wherein the average price last year is 100 and standard deviation is 5. It's the same as the stock A. Now, in which of the two, okay, would be a better investment? Okay, now remember, the lower is your coefficient of variation, the better is your risk return trade-off. So if you are investing, okay, you would opt to consider, okay, wherein you will have better risk return trade-off. So we have to compute for the coefficient of variation of both stocks. We will do the comparison between the two. That is the coefficient of variation of stock A, all right, is given to be, our standard deviation is 5, okay, divided by our mean, which is 50. We multiply it by 100%. Therefore, the coefficient of variation of stock A is 10%. Okay, now what about stock B? In stock B, the standard deviation is also 5, okay, with a mean of 100, and we multiply it by 100%, we get a coefficient of variation, which is 5%. So comparing the two, we have a lower coefficient variation in stock B. So that means to say, of the two stocks, okay, I will be investing in stock B because I have a better risk return trade-off indicated by a lower coefficient of variation of 5% as compared to the coefficient of variation in stock A, which is 10%. Okay, so I will be investing in stock B. All right. Now, we continue. Okay. The next application that we have is what we refer to as a standard score, which tells the relative location of a particular raw score with regards to the mean of all the scores in a given series. Okay, which is actually a transformed raw score, because we will be expressing this into what we refer to as our Z score, okay, or what we refer to as our standard score, which is expressed in terms of standard deviations or units, okay, from the mean. Right now, we may possibly end up with a positive standard score, okay, or with a negative standard score. Now, keep in mind that a positive standard score will indicate, okay, that the transformed raw score will be above or higher than the mean. Okay, we will see that in our formula later on. And a negative standard score will indicate that the given raw score is actually lower than the mean. Okay, how is that so? So if we're going to look at our formula, okay, so the formula for our Z score or for the standard score is usually used to compare observations in 2 or more different distributions of raw scores, which have different means or different standard deviations. Okay, so the X that we have here, this is our raw score. Okay, and the X bar that we see, okay, recall that our X bar here is our mean. All right, and our S here is our standard deviation. Okay, now as what we have indicated, there are 2 scenarios for the value of Z. Okay, that is if we have a positive Z score. Okay, so if the Z score is positive, looking at our formula, that means to say our X value here should be greater than our mean. Okay, so take note of that. So we will end up with a positive Z score, okay, if in this case, X is found to be greater than our mean. Consequently, we will have a negative Z score, okay, if in this case, all right, our raw score will be less than our mean. Okay, that's because if our raw score is less than our mean, so when you subtract these two, you will end up with a negative value. Okay, now let us illustrate the concept of the standard score or the Z score, okay, by this example, wherein I have embedded a video clip. However, in this video clip, there is a correction which I intend to present in a while. Okay, so kindly pay attention to this short video clip, all right, wherein this explains, okay, in the data that we have in this example, wherein Ruben got a final grade of 85 in both English and physics. So the mean final grades of this class in these two courses is 80 in English and 75 in physics. So if you look at it, higher grade is in English than in physics. However, there are added information when the standard deviation is 12 for English, and in physics, the standard deviation is 10. Now we are asked, in which subject was his academic performance better in relation to his class? We will answer that question in this video clip, so kindly pay attention.
Okay, so let us consider the example that we have here. That is, Ruben got a final grade of 85 in both English and physics. And the mean final grades of his class in these two courses are 80 and 75, with standard deviations of 12 and 10 respectively. Okay, so we are asked in which subject was his academic performance better in relation to his class. Okay, so that means to say his grade in English is 85. The same is true with his physics grade, which is also 85. Okay, so let me have our x, which is equal to 85. That is for both English and physics. Now, if his grade was 85 in English and also in physics, all right, given the following data values in terms of the mean, the standard deviation, how can we say, or how do we determine in which subject did he perform better, okay, in relation to his class? So in this case, that means to say we're going to standardize, okay, or we will get the standard score of his grade of 85 in relation to the performance of his entire class. Okay, so let us compute for the z-score in English. Okay, so let's have that. So let us consider the z-score in English. So let me make use of the subscript of E to indicate that we're computing for the z-score of his 85 grade in English. And using our formula, we will have x here, or our raw score in this case is 85. We subtract the mean score, which is 80, and we divide it by our standard deviation, which is in this case, in his English class, the standard deviation is equal to 12. Okay, so what we will have is that 85 minus 80, and then we divide that by 12. What we will get is, this will be equal to 0.33.
Okay, now I would want to make a correction here, because 85 minus 80 is 5 over 12 is not equal to 33, but instead that is equal to 0.42. Okay, so let me round it off. Okay, and the z-score of his grade in English is actually 0.42. Okay, so kindly make the correction, please. All right, let me continue with this video.
Okay, so that means to say his 85 grade in English, okay, is 0.33 standard deviations above the mean.
All right. I would want again to make that correction. Instead of saying there, that would be 0.33 standard deviations above the mean. Okay, what should be indicated here is that his grade of 80 in or his grade of 85 in English is actually 0.42 standard deviations above the mean. Okay, above the mean grade of his class, which is in this case is 80. All right, so let me continue with the video.
Okay, all right, we will go back to the interpretation in a while. Now, let us also compute for the standard score of his grade of 85 in physics. So let me indicate our z-score with a subscript of physics. Okay, so let me just make use of this one. So let me just use P for physics. All right, and his grade is 85 also. We subtract the mean of his entire class, which is 75, and the standard deviation of all of the scores in his class would be 10. So 85 minus 75 over 10 will give us a standard score which is equal to 1. Okay, now how do we interpret this? All right, so that means to say his score of 85 in physics, okay, is 1 standard deviation above the mean. Okay, now how do we say or how do we indicate that it is above or below the mean? Okay, so when the z-score is positive, then that means to say the raw score is greater than the mean. Thus, the value that you will have here would be positive. Okay, however, if the z-score is negative, then we would say, or that will indicate that the raw score of x will be lower than the mean. Okay, thus you will end up with a negative z-score. Okay, now, so going back to our example, so of the two subjects, in which subject did he perform better? In English, his grade of 85 is just 0.33 standard deviations above the mean.
Okay, again, his grade of in English of 85 is 0.42 standard deviations above the mean. Okay.
However, his 85 grade in physics is 1 standard deviation above the mean. So that means to say, he performed better in physics. That's because his grade of 85 is 1 standard deviation above the mean as compared to his grade of 85 in English, which is just 0.33 standard deviations above the mean. Okay?
All right. Again, his grade in English is 0.42 standard deviations above the mean.
That is how we interpret the concept of the standard score, or also referred to as the z-score. Okay, so I hope that is clear.
All right. So kindly don't forget the correction I made here having to do with the standard score of his grade in English, which will be equivalent to 0.42 standard deviations above the mean, as compared to his z-score in physics, wherein his grade of 85 is actually his grade of 75 is actually 1 standard deviation above the mean. So if you're going to look at it, even though his actual grade in physics is lower than in English, which is his physics grade is 75. Sorry. Again, let me correct that one. Looking at it, his grade in physics and in English are both equal to 85. However, the performance of his class in English, the mean grade is 80, and the performance of his class in physics is 75. Okay, so even though his grade in both English and in physics are the same, all right, by having computed for the z-score, when we standardize the score, we ended up knowing that his performance in physics is actually better as compared to his performance in English, because his grade of 85 in physics is actually 1 standard deviation above the mean as compared to his grade of 85 in English. Okay, so I hope that's clear. All right. Now, we proceed, okay, to the last part of this discussion, wherein we apply what we refer to as the empirical rule. Okay, or in some reference materials, it is referred to as the 68, 95, 99.7 rule. Okay, now we will be presenting two scenarios here, wherein if the data is taken from the population, okay, so we make use of the parameters mu to represent the mean, okay, and our standard deviation will be represented by sigma, okay. So if a variable x follows a normal distribution, so take note of that. It is important that the assumption is that they are normally distributed, or in that case, they follow what we call the bell-shaped curve. Okay, therefore, okay, 68% of the entire population, okay, will be within 1 standard deviation above the mean, and that is indicated by this notation. Okay, and also 95% will be within 2 standard deviations above the mean. Okay, and 99.7% of the entire population will be within 3 standard deviations above the mean. Okay, and let me illustrate that clearly later on. Okay, and it is actually simpler as it seems to be. Okay, sige. Now let us continue. If our data is taken from the sample, then we're going to make use of our statistic X bar for the mean and S for the standard deviation. Okay, and it will indicate that 68% of the entire sample, okay, will be within 1 standard deviation. Okay, and about 95%, okay, of the entire sample will be within 2 standard deviations. Okay, and also 99.7% of the entire sample, okay, will be within 3 standard deviations. All right. And to illustrate that further, okay, to visualize what we mean by the 68, 95, and 99.7 rule, okay, referring to this diagram, okay. So here, this is corresponding to 68% of the distribution are within one standard deviation above the mean, okay, and one standard deviation below the mean. Okay, so if you notice, we see a negative and a positive value. So if it's a positive value, it is found to the right of the mean, or it is above the mean. If the value in this case is -1, it will indicate it is to the left of the mean, or that is one standard deviation below the mean. Okay, and that will comprise 68% of your entire data, okay, or in this case, entire sample, because we made use of the statistic in X bar, will be within one standard deviation. Okay, in the same manner, right, we will have two standard deviations, okay, to the right of the mean, okay, and also two standard deviations to the left of the mean, which will be approximately 95% of your data are found here. Correspondingly, okay, we say we have three standard deviations to the right of the mean, okay, and also three standard deviations to the left of the mean. Okay, and that will be approximately 99.7% of your entire sample. Okay, but if you notice, what is this? Okay, this region that we have here, right? Because by a theorem, we indicate that approximately 100% of your distribution are found within or under your bell-shaped curve. So if within three standard deviations, okay, from here to here, this will comprise 99.7%. That means to say there is a remaining of 0.3%, which will correspond to, this is 0.15%, okay, and this is also equal to 0.15%. Okay, so that if we're going to sum up everything, 99.7% plus these two percentages we see in the far left and far right of the distribution, that will be approximately equal to 100% of your data are found under the normal curve or under the bell-shaped curve. Okay? Now, this is what we have indicated, all right, that 68% of the data would fall within one standard deviation. When we say within one standard deviation to the right and one standard deviation to the left of the mean. Okay, and that is 95% of the data would fall within two standard deviations, meaning when we say within two standard deviations, within meaning above and below, or that is to the right and to the left. So two deviations to the right and two deviations to the left. And also 99.7% of the data would fall within three standard deviations. That is three standard deviations to the right and three standard deviations to the left of our data. Okay. And let's consider the following, all right? But I need you to pay attention to the percentages that we will see, okay, in this diagram, because it will be consistent. It will be the same values, okay, every time we make use of the empirical rule. Okay, but what will vary will be the values that we will encounter in the interval or along the x-axis or along the horizontal axis. So if this is 68%, then that means to say we have 34% to the right or within one standard deviation. That is 34% one standard deviation above the mean, and also 34% one standard deviation to the left of the mean. And that will be equal to 68%. Okay. Okay, what we have indicated for the bell-shaped curve or for the normal curve is that it is a symmetric distribution. So when you say symmetric, okay, what we see at the right is a mirror reflection of what we have at the left. Okay, so they are mirror images of one another. So if we have 34% to the right, then we also have 34% to the left of the mean. Okay, and that will be equal to 68%. Consequently, two standard deviations above the mean, okay, will give us a total of 47.5, okay, and two deviations to the left of the mean, that will also be 47.5%, for a total of 95%. So 95% was divided into two. You will have 47.5%, which is two deviations to the right, and 47.5% two deviations to the left of the mean, okay? And also, for within or falling within three standard deviations, okay, that is a 99.7% will be divided into two. We will have 49.85% to the right, or three deviations to the right of the mean, okay, and correspondingly, 49.85% of the data, okay, are found 3 standard deviations below the mean. Okay, that is for a total of 99.7%. That's why earlier we pointed out that what we will have here, this is 0.15%, and this is also equal to 0.15% because they are symmetric. Okay, so we keep in mind what we see at the right will be reflections of what we see at the left and vice versa. Okay, now we proceed from here. Let's put that concept of empirical rule, okay, by the example that we have here. Okay, that is in a preparation for a clearance sale at a women's apparel shop. 2,000 brochures were placed in readdressed envelope. They were sealed and stamped. And this process took an average of 7 seconds per envelope with a standard deviation of 1.8 seconds. And assuming that this population of times is approximately bell-shaped, this is very important, okay, because it has to be stated in the problem that we are assuming it is normally distributed or it follows the shape of the bell, okay, so that we can utilize the empirical rule. Because the moment your distribution is not normally distributed, okay, meaning they do not follow the bell-shaped curve, then we cannot use the empirical rule. Because remember the empirical rule, we utilize ang bell-shaped curve, okay? So take note of that. So the moment the distribution is not normally distributed, not following the bell-shaped curve, then automatic, we cannot utilize the empirical rule. Okay, so going back to this example, let me demonstrate that in this video clip. Okay, so this is the following that is required of us from this particular example. So kindly pay attention to this one.
Okay, so let us proceed to what we refer to as the empirical rule, or also referred to as the 68, 95, 99.7% rule. Okay, now here, we may take our data coming from the population. So if that is the case, we will have to consider the population mean and the standard deviation, or mu and sigma. Okay, or if the sample, or if the data values are taken from the sample, then we will make use of X bar for the sample mean and S for our standard deviation coming from the sample data. Okay, now, however, we have to keep in mind that the distribution must be assumed to be normally distributed so that we can make use of the empirical rule. Because the moment your distribution is not normally distributed, then we could not make use of the empirical rule. Okay, so what is the purpose of the empirical rule? How do we make use of the empirical rule to make some conclusions or interpretations of the given distribution that you have? So here, in the normal curve, the mean is found at the center of the distribution. Okay, and we say that 68% of the entire distribution, okay, would include or is found within one standard deviation. When you say within one standard deviation, meaning to say one standard deviation above the mean and one standard deviation below the mean. Okay, because if this is your mean, one standard deviation above the mean is this one. If this is the mean, one standard deviation below the mean is that we're going to the left. So that means to say, what we have there is approximately 68% of your distribution is found within this region. So let me indicate that. So meaning to say, within this region, okay, this one would be 68%. Alright, since this is symmetric, the 68% will be divided into two equal parts. So that means to say, we have 34% is found in this region, that is one standard deviation above the mean, okay, and one standard deviation below the mean, that is also 34% of your distribution. Okay, so that we will have the total there, which is equal to 68%. Alright, now, the next part of the rule is that 95% of the distribution, okay, or the entire distribution is found within two standard deviations. That means to say, two standard deviations above the mean, or two standard deviations to the right of the mean, okay, and two standard deviations to the left of the mean, or two standard deviations below the mean, would give us an approximate of 95% of your distribution is found within this region. Okay, so if this is 95% ang total, and we already have 68% in this case, that means to say 95 minus 68, okay, that will give me the remaining percentages in these two regions. Okay, so let me have that. So two deviations to the right of the mean and two deviations to the left of the mean, that will give me an approximate of 95% of your distribution is found within two standard deviations above and below the mean. Okay, that means to say, if this is 95%, all right, the 95% will be divided into two equal parts. Okay, so we will have 95 divided by 2. That means to say, this region that we have here, two standard deviations above the mean, will be equivalent to 47.5%. But I already have 34%. So that means to say the 47.5% minus the 34% that I have will give me, the remaining part here will be equal to 13.5%. Same is true with this region, which is two deviations above the mean. The total is 47.5, but you already have 34%. So that means to say this is equal to 13.5%. Okay, in the same manner, when we say 3 standard deviations above the mean, okay, so that means to say if this is your mean, 3 standard deviations above the mean, okay, and 3 standard deviations below the mean, that is 1, 2, 3 standard deviations below the mean, approximately 99.7% of your distribution is found in this region. If that is 99.7%, and we already have 95% covered here, ang remaining would be equal to 4.7%. So si 4.7% will be divided into 2 so that it will occupy these two regions that we have here. And that will be equal to 2.35%. And this is also 2.35%. So that if we sum up everything here, that will be equal or approximately equal to 99.7%. Okay, now, however, all right, under the curve, okay, we assume that 100% of your distribution is found below this curve. That means to say, ang total dapat under the curve should be equal to 100%. But found within 3 standard deviations above and below the mean is just 99.7%. That means to say we still have 0.3%, which is found in this region and also in this region. So si 0.3% will be divided into 2. That's because we have 2 regions to the right and to the left of the mean. So meaning to say this will be equivalent to 0.15%, and this will also be equivalent to 0.15%. So that if we're going to sum up all the percentages under the curve, that will be equal to 100%. Okay? Now, say for example, all right, our main concern will be the intervals that we see along the horizontal. Okay, so what we have when we say 1 standard deviation above the mean, that is mu plus 1 times standard deviation. Kung 2 deviations, that is mu, this is mu, okay, plus 2 times sigma, or 2 times the standard deviation. The same is true when we say 3 standard deviations to the right of the mean, that is mu plus 3 times the standard deviation. Okay, now let us consider our example. Alright, so that we will better understand the concept of the empirical rule. So say in our practice exercise, in preparation for a clearance sale at a women's apparel shop, 2,000 brochures were placed in readdressed envelope, sealed and stamped. So this process took an average of 7 seconds per envelope with a standard deviation of 1.8 seconds. So we are assuming that this population of times is approximately bell-shaped. So we are asked to find the number of envelopes that took within the following values given, or the number of seconds to prepare the envelopes. So in our given data, our population is 2,000 brochures, okay, and the standard deviation, our population is, that is our big N. So our big N is equal to 2,000, and our mean will be equal to, it took them 7 seconds per envelope, okay, to process it. So that means to say our mean is 7 seconds, and the standard deviation would be 1.8 seconds, okay. So what will happen to the interval that we have here? What will actually not change are the percentages. Those are fixed. Okay, so basically I don't memorize all of them. I simply just derive these percentages by the fact that 68, 95, and 99.7% are found within one standard deviation from the mean, and 95% within 2 standard deviations from the mean, and 99.7% within 3 standard deviations from the mean. Okay? Sige. Now, we will come up with the intervals that we have here based on the values that we have for the population, the mean, and the standard deviation. So the mean, as what we've indicated, is found at the center of the distribution, and that is equal to 7 seconds. Our standard deviation is 1.8. Okay? So that means to say, one standard deviation above the mean, what we need to do is simply add an interval of 1.8. So 7 plus 1.8 will give me 8.8. In the same manner, another or 2 standard deviations from the mean, I'm simply going to add 1.8 to the previous interval that we have here. So 8.8 plus 1.8 will give me, that is equal to 10.6. Okay? In the same manner, 10.6 plus 1.8 will give me 12.4. Okay, what about the values that we have to the left, or one standard deviation below the mean? So that is, we will be subtracting an interval of 1.8 from the mean. So 7 minus 1.8, that will give me 5.2. So again, 2 deviations to the left of the mean. We are going to subtract 1.8 from 5.2. Okay, what will we have? That is 5.2 minus 1.8 will give me, that is 3.4. In the same manner, we need to subtract another 1.8 from 3.4, and we will get, that will give us 1.6. Okay, we will make use of these intervals to answer what is required in our example. So we are asked, okay, find the number of envelopes that took them from 5.2 seconds to 8.8 seconds. Okay, so from 5.2 to 8.8 seconds, the equivalent percent is 34% and 34%, that will be equal to 68%. So that means to say, for letter A, that will be 68% of our population of 2,000. We're not yet done. That's because we are asked of the number of envelopes. Okay, so in this case, we are going to get the 68% of 2,000, and what we will have is, we multiply 2,000 times 0.68, or the equivalent in decimal. That will give us 1,360 envelopes. Okay, were processed, okay, from 5.2 seconds to 8.8 seconds. Okay, I hope that's clear. Alright, let's proceed with letter B. Okay, with letter B, we are looking for the number of envelopes that took them more than 10.6 seconds to prepare. So 10.6 is here. When I say more than, I'm going to get the percentage or the percent to the right of that. Okay, so I have 2.35 plus 0.15%. That will be a total of 2.5%. Multiply it with our population because we're asked of the actual number of envelopes. So in that case, that is 0.025 times 2,000. You change this into decimal. That will give you 50 envelopes are processed more than 10.6 seconds. Okay? Let's have the last item. For letter C, how many envelopes were processed less than 5.2 seconds to prepare? So see, 5.2 seconds is here. When we talk of less than 5.2 seconds, we will get the values to the left. So that will give us, we will sum up the percentages to the left of 5.2 seconds. That is 13.5% plus 2.35% and 0.15%. That will be equal to 16%. So mean to say, we will get 16% of 2,000, and that will give us equal to 320 envelopes. Okay? So if you're asked of the actual number of a certain item or a certain category or certain variable in your given distribution, do not forget, the moment you have determined the corresponding percent for that particular interval, multiply it with the population. Okay, so our population here is 2,000. However, if you're simply asked to give the percent or the proportion, then you simply have to indicate the percent. You don't have to multiply it to the population if you are not asked of the actual number of that certain variable. Okay, so I hope the concept of the empirical rule is clear to you. Okay?
All right. So basically, that's the coverage of the concept of empirical rule. And keep in mind how this example was done, because it will be similar to what you will encounter in our learning path. All right. And what I have here are the items indicated in the learning path. So I hope you will find time to finish them. And this will be the end of my presentation. Okay.